Okay, I'd like to thank the organizing committee for inviting me. I'd also like to acknowledge support from FeedWorks for my travel support, and then my colleague Mike Allen, who helped with some of the thinking that has gone into this because we've worked together for 30 years. I always have a problem with knowing where to point when we have two screens, so I'm going to be partial to this side of the audience. I guess before I start, I'd just like to know how many people are actually farmers working with cows every day, have farms? All right, a lot of you. And how many are support industry? Students can raise their hands on this one too. Yeah, so okay, so that's everybody, I hope. So my perspective on the topic comes from the U.S., where we don't usually graze cows, and I just want to start off with that. I understand biology. I understand the problems with two things I'll talk about today, and that's metabolizable energy and crude protein values and their shortfalls. I don't always understand everything about your system. However, we do graze our heifers at our research farm, and I did grow up on a dairy farm in Iowa where we fed basically a partial mixed ration, and then we grazed cows for a half a day in the summer. The reason we don't graze more often is because we have to deal with winter. I know you have your time of year when there isn't much grass. For about half of the year, that's what we have, and for part of that, the grass can't even be seen because it's covered with snow. And I really appreciate that I got invited to Australia in February, and I don't have to be there now. So, because we have to feed harvested forages for most of the year, there's been an uptick in the number of people who say, you know, I might as well feed harvested forages all year. And there's a good reason for that, and that is because we love a system where we can have complete control of our cows. So we feed a total mixed ration. A cow gets a little bit of everything in every bite all day long, as opposed to feeding grain morning and evening milkings, where suddenly she has a big bunch of fermentable starch coming into her rumen twice a day that changes everything, and it changes the way that I think about feeding. We also can have these nice big barns that are very comfortable, fans to keep the cows from being heat stressed. Even in Michigan, we can have heat stress in our summers, and the cows are comfortable in there. Having said that, I know there are a lot of advantages to grazing cows too, and in fact, to a certain extent, I lament the fact that few of our cows actually spend as much time on grass as they once did. But the reason that we've switched to TMRs is because of this. As we switch to TMRs, we've had more control over what the cows eat. We've had better control over increasing dry matter intake, better control over everything, and because of that, we could increase production. And as we increase production, lifetime gross efficiency of cows has gone up. Average production in the U.S. is somewhere around 10,000, 11,000 liters per cow per year. I realize that's not solids, okay, those are Holsteins. So it's probably 3.5% fat, 3.2% protein. But as we've increased productivity, we've increased efficiency, and generally, unless you go crazy buying a lot of stuff because you had extra money to spend, increased efficiency, feed efficiency means you have more money in the bank. So that leads, so my point on the last slide is if you can get cows to eat more energy, I guarantee they will almost always produce more milk, and that will be to your advantage. However, when it comes to thinking about getting more energy into a cow, how should we do it? We can feed supplements. Okay, and in this scenario I said, okay, we have 3 supplements we could use. I realize maybe the barley's a little low on energy, but you have barley's like this. I took these values from the Dairy Australia website. So ME values, crude protein values, price per ton, and I calculated out the price per unit of energy, which I put in gigajoules, which Hugh gave me a hard time about because he had never heard of gigajoules, but 1,000 megajoules is a gigajoule, just like on a computer, gigabytes. Okay, so price per unit of energy, the barley is clearly the cheapest. That's the right one to use, right? Well, not necessarily, because we have to think about things a little bit more complicated. It's not nearly that simple. First off, the energy value of feeds is a guess, and it's often wrong. How do we come up with an energy value of 13.3 for maize grain? It's a bunch of equations that are based on assumptions that are based on Well, you can come up with lots of different equations to come up with an ME value, and there are different ones that exist for the very same grain sample. Moreover, I should just point out, when we do these energy values, they're always on a finely ground sample. Do you feed that? Okay? No, of course not. So these energy values are very misleading. The crude protein value of a feed is really quite accurate because it's simply nitrogen times 6.25, but it's not really what the cow cares about. So the two things that we use to buy and sell feed are really, well, they're useful. I pay attention to them, but they're not that helpful. Energy and protein in feeds, not only what I just talked about, but the energy and protein in feeds can alter intake and how feed nutrients are used, independent of what these values are. Even if I could get these numbers right, they still have problems because feeds affect intake and partitioning. Okay, so the NE, I'll go through those real fast. So the NE value of a feed is always a prediction. We do know the gross energy value of a feed, usually, or at least we could measure that in a lab. But first it has to be digested, and then it has to be converted to what we call metabolized energy. We have fecal energy losses, urinary energy losses, gas energy losses, and I would like to point out that even though we talk about metabolizable energy, really it would be more correct to say metabolized energy. What actually happens in the cow is what I care about, and can I predict it? And the answer is often not that well. So, we can look at our four main classes of nutrients: fiber, starch, protein, fat. They have gross energy values that I'm fairly confident about, 4, 4, 6, 9. They're converted to ME, and the fiber's worth somewhere on the order of 1 to 3, starch 3 to 4, protein 3 to 5, fat 5 to 7. And if we knew the digestibility values, we could come up with these fairly accurately. However, they all depend on things like digestion, how much gas and energy loss occurs, and starch in the diet can affect fiber digestion, and it can affect protein metabolism. And protein in the diet can affect fiber digestion, and fat in the diet can affect how much methane is lost. So these things all interact. Coming up with one single ME value for a feed is just not adequate. Okay, we cannot predict the ME value of a feed without knowing the whole diet and its level of intake. Each nutrient class alters feed intake and partitioning. These effects can not easily be made into equations, and in fact, I should just cross out the easily and say we can't put these into equations. You need to watch your cows and try to understand what the cows are telling you. That is the only way to try to maximize energy intake so that you can maximize milk production efficiency and hopefully profitability. Crude protein. We feed crude protein, nitrogen times 6.25, but some of it's degraded in the rumen and some of it's not. The stuff that is degraded in the rumen is great, okay? Microbes use it. They make microbial protein as they grow and divide and thrive in the rumen, and some of them get flushed down the tract. But the RUP that's in the rumen is important because we simply can't get enough microbial protein from most feeds for high-producing cows to meet all the needs of metabolized protein for milk and body proteins. Consequently, we need some rumen undegraded protein in our diets. Where are you going to get it from? Your pasture actually is not that good at RUP. It's mostly going to be degraded protein. Some of it's not even true protein. So we can get caught up with numbers. Okay, we need ME, we need CP for milk and maintenance and physical work. And I've already said it's difficult to predict ME. CP is really not all that useful. And the responses, I want to say, are more important than the actual values that you get from a feed lab. Okay, so let's think about this a little bit more biologically. Okay, so we feed starch, fiber, proteins, lipids. Okay, here's what we want. We want a lot of milk, but we recognize that these things are also partitioned to body tissues, maintenance, and physical work. So the first thing we need to think about is what happens in digestion. Okay, so some feeds are digested in the rumen. Okay, in particular, fiber and a lot of the starch will be converted to acetate, propionate, and butyrate, the volatile fatty acids. And but we also have a little bit of glucose being absorbed. We have amino acids and lipids being absorbed from the small intestine. And if we don't digest things, fiber, for example, in the rumen, it can also make it to the hindgut, where it could be digested as well. These things, everything except for the lipids, all travel to the liver. And at the liver, there's metabolism that happens. Some of them go right past the liver, glucose for example, but a lot of them get shunted into different compounds. And in particular, we're interested in propionate, which comes from starch fermented in the rumen, because it's used to make glucose. And glucose is what we need to make